All right, I guess it's time to start. Let's go ahead and do this thing. So verify that this function u of xyt equal to cosine of x minus a constant times t plus sine of y minus a constant times t satisfies the wave equation del squared u del t squared. So this the second partial derivative of u with respect to t is equal to the constant squared times the sum of the second partial derivatives of u with respect to x and y respectively. So if I'm going to do this thing, I'm just going to kind of calculate both sides of this equality and hopefully see that they end up being the same. I think the last problem on the homework assignment that I posted the solutions to, there was a similar kind of problem asking you to show that like these two things were equal. And if you looked at it, you saw that it was super messy. Like really, I don't remember exactly what problem it was. It was like it was from 9.2. And it was something like, oh, sure, of course, yeah, definitely. Do that too, just to make it easier. Let's see, 9.2. 1 second. Sorry, I was just reminded about this kind of terrible, messy problem. Let's see, 9.2, I believe it was. Yeah, it's problem 70 from 9.2. This diffusion equation thing. Let me zoom in here for just 1 second so you all can see. It was showing that the derivative of this with respect to t, the partial derivative of that with respect to t, was equal to the constant d times the second partial derivative of c with respect to x. And what I did the same kind of thing I'm gonna do here, which is finding both sides and then really manipulating each side to kind of get to a point where they look the same. And it was, if you look at the algebra there, I was like, oh my God, it's taking forever. And I finally like was just started working on one little part of it because I got tired of writing the whole thing over and over and over again, which is fine. You just have to be clear about what you're doing. So sometimes showing these things are satisfying an equation, some differential equation, can be a little bit tedious, a little bit tricky algebraically. So let's start with the left-hand side. So I'm going to find the second partial derivative of u with respect to t. I'm going to start by finding the first partial derivative of u with respect to t. I should raise this up here. So I'm going to find del u del t. So taking the derivative of cosine of some stuff, I'm going to get negative sine of that stuff multiplied by the derivative of the inside stuff with respect to t. The derivative of x is 0. The derivative of negative c times t is just going to be negative c. Plus, same deal over here. Derivative of sine of some stuff is going to be cosine of that stuff times the derivative of the inside stuff with respect to t again. The derivative of y is 0. The derivative of negative ct is once again negative c. You could distribute the minuses here, but it's not really that important to make it easier. And we should probably just wait till the second derivative. But if you wanted to, you totally can make this a positive c times sine of x minus ct and a minus cosine or c times cosine of y minus ct. But I think we just wait. So now let's find the second derivative, del squared u del t squared. That's going to be, so this negative c here is just a constant multiple. It's just going to hang out. So I'm really just thinking about differentiating negative sine of some stuff. I'm going to get negative cosine of that stuff times the derivative of that inside stuff again, which is still negative c like it was in the previous step. I'm just going to get negative c times another negative c, or I would probably get negative c squared. Plus the derivative of cosine of some stuff is going to be negative sine of that stuff times the derivative of the inside, which again is negative c. So I'm again getting a negative c squared. And now I am going to simplify this just a little bit. I see that overall here I have a negative cosine times a positive c squared here. So I'm going to get a negative c squared times cosine of x minus ct. And here it's going to be a negative c. It's going to be also a negative sine times positive c squared. So it's going to be a minus c squared times sine of x minus ct. And yeah, I could factor out a c squared, but I don't really need to see that things are going to work out the way they're going to work out. So now let's do the other side. Let's look at c squared times del squared u del x squared plus del squared u del y squared. And how I would probably do this is first by just finding these second partial derivatives. So let's go ahead and find del u del x. So del u del x is going to be, so now we're differentiating with respect to x. Ooh, hopefully I didn't make a dumb mistake. No, I didn't make a mistake. So the derivative with respect to x, the derivative cosine of some stuff is going to be negative sine of that stuff. And now the derivative of the inside is 1. Derivative of x is 1, derivative of CT is 0. Plus the derivative sine of some stuff is going to be anybody? It's going to be 0. Because what am I differentiating with respect to? X. And are there any x's in there? Definitely not. So as far as x is concerned, that's a constant. So we don't get any, or we get the derivative that is 0. And then similarly, let's write it over here. Del u del y is going to be the derivative of that part, because that part doesn't have any y's in it. So their sine some stuff is going to be cosine of the inside stuff. And then if we multiply by the derivative of the inside with respect to y, we're going to get 1. All right, let's find the second derivatives. So del squared u del x squared is going to be negative cosine of x minus ct times 1. Del squared u del y squared is going to be, the derivative cosine is negative sine, so I'm going to get negative sine of y minus ct. And then I'm going to write this equation. So c squared times del squared u del x squared plus del squared u del y squared. Let's write it out. C squared times del squared u del x squared plus del squared u del y squared is equal to c squared times negative cosine of x minus ct minus sine of y minus ct. And I think at this point, I don't need to distribute the c squared here or factor out the c squared there to see that, oh yeah, those are the same. Which shows that c squared times del squared u del x squared plus del squared u del y squared is equal to del squared u del t squared. Kind of a little bit tedious, but that's probably the fastest way to do it. Yeah, question.
Is that an error at the top where it says negative c squared times the blue, right, or where it's like same? Because it says minus c squared sine x minus c squared. Isn't it supposed to be y minus c squared?
Oh, it is. Yeah. No, good catch there. That should be a y for sure. Thank you. Yeah, speaking of that, I noticed on Wednesday from the notes, it looked like when he was writing these equations at the end of class, it looked like he wrote like del squared y, del y squared instead of del squared u, del y squared. I don't think he meant to do that. It was just sometimes people make little errors. So, but thank you. I appreciate you catching that. Other things to say here. Okay, let's go ahead and review that quiz question, which was finding the second partial derivatives of the following function. I should get some paper. Let's go ahead and look at, let's see, the question was, so given f of x comma y equal to sine of x squared times natural log of y squared, find all the second partials. So when I read that, I should really say set find all second partial derivatives. When I read that, I take that to mean I need to find all 4 of them. I have to find del squared f del x squared, del squared f del y squared, del squared f del x del y, and del squared f del y del x, even though they should probably end up being the same. Unless I'm wrong. But I imagine that's what you were expected to do if that was the question. But before we can find any of those things, we have to find the first partials. So before I even find any first partials, I would probably choose to make the following adjustment. I would rewrite my function as sine of x squared times 2 natural log of y. And I would probably actually even bring that 2 out in front, right, as 2 times sine of x squared times natural log of y. It's not required, but I do think it makes it a little bit easier. Even if you didn't do that, your answer should come out the same either way. I'll just point out off on the side here just so you all can see it. Not on the side here, on a different piece of paper. I want to mention here, right? Whether you take the partial derivative of 2 natural log of y and get 2 times 1 over y, or you take the partial derivative with respect to y of the natural log of y squared and get 1 over your stuff times the derivative of your stuff, the answer is still 2 over y, either way you slice it. So it doesn't actually, I mean, it matters in that it makes it easier to find the derivative, in my opinion, but if you don't do that simplification and you still do the right derivatives takings, you will get to the same correct answer. Okay. So I always start with x because it comes before y alphabetically. No good reason. So when I'm looking at taking the partial with respect to x, I'm noting that 2 and natural log of y are constants, and I'm just differentiating sine of some stuff. So I'm going to get 2 times cosine of my stuff times the derivative of that inside stuff, and then still times the constant natural log of y. And since I know I'm going to have to take a second derivative here, it is in my interest to simplify this and make it a little bit easier to deal with. So I'm going to rewrite this as 4 times x times cosine of x squared times natural log of y. Taking the partial with respect to y, I'm going to get, well, now the sine of x, the 2 sine of x squared. I'm going to put that in a box so I can keep remembering that that's what my f of xy is equal to. It's easy to see for me. Taking the partial with respect to y, the 2 times sine of x squared is the constant that's hanging out, and the derivative of the natural log of y is 1 over y. Now we have a choice here. We can either rewrite it as 2 sine of x squared over y, and then probably have to use the quotient rule at some point in the future. Or I would probably prefer to write it as 2 times sine of x squared times y to the negative first. So then when I take the derivative with respect to y again, I don't have to use the quotient rule, I can just use the power rule. Usually, if you can write something not as a fraction, it's often a good thing to do. Not always, sometimes it's better to write it as a fraction. Okay, so we found the first partials. Any questions? Also, before I forget, for those of you on Zoom, those of you on Zoom are also welcome to ask questions, but here's the attendance form for anyone that's joined, in case you didn't already do it. Cool. All right. Continuing on, let's find fxx first. fxx is going to be kind of a pain, because if I look at fx, which is 4x times cosine of x squared times natural log of y, I am going to have to use the product rule. I've got 4x as a function of x, and I do kind of think of it, right? I'm not really thinking about 4 out in front anymore. I'm really thinking of it as being attached to the x just because it's easier. You can do whatever you like, but I think of it as, oh yeah, one of my functions is 4x, one of them is cosine of x squared, and then you've got the constant natural log of y that's just going to hang out. So taking the derivative of this using the product rule, the derivative of 4x is 4 times cosine of x squared plus 4x times the derivative of cosine of x squared is going to be negative sine of my stuff times the derivative of my stuff. All of that still gets multiplied by the constant that's hanging out, which is natural log of y. Should I simplify this? Only if I'm asked to, really. But like if this is the quiz and we're only asked to find the second derivatives, and they didn't tell us to simplify it, I would probably leave it like that. If you want to simplify it, you can make it. I mean, there's not a lot of simplifying can be done here. You can write it as 4 cosine of x squared, and then 4x times 2x times the negative 1 is going to be a negative 8x squared times sine of x squared, all that times natural log of y. I don't think that's necessary, but maybe it is. That was probably the messiest one we're gonna have to do. The rest of them should be less terrible than that. So let's find FYY. All right, so now looking at my FY, that's equal to 2 times sine of x squared times y to the negative first. I'm just differentiating that with respect to y again, which is nice. The 2 sine of x squared out in front is just a constant. The derivative of y to the negative first is -1 times y to the negative second. Not too terrible. If I was going to simplify this, I would probably try to make all my powers be positive. So if I was going to simplify this, I would probably write it as -2 sine of x squared divided by y to the positive second. I left the negative out in front, and I brought the y down to be, instead of y to the negative second, y to the positive second. Okay, 2 more to go. So let's do fxy, which I will remind you is the same as del squared f del y del x. Meaning you do the partial with respect to x first. There's my partial with respect to x. Then you take the derivative of that with respect to y. That's not too bad. The 4x cosine of x squared is just going to hang out. And then we're going to multiply by the derivative of the natural log of y, which is 1 over y. Not too bad at all. Assuming it comes out the same the other way. So let's do the other one. Let's do fyx. Now, what I'll point out here is if you were strapped for time, or you just looked at the other one and it looked really, really gnarly, you could probably get away with just saying this is equal to 4x cosine of x squared times 1 over y. That's probably not a bad idea. But if I'm actually looking at it, I look at fy, I've got 2 sine of x squared times 1 over y. So the derivative of that with respect to x is going to be 2 times the derivative of sine of x squared is cosine of x squared times the derivative of x squared times the 1 over y that's hanging out. And yeah, that's the same. That's going to be 4x times cosine of x squared all divided by y, which is probably how I'd write this one as well. 4x times cosine of x squared all divided by y. And those match, which is great. They should match. Unless your function is super funky. I don't know if you've looked, but he definitely somewhere on Canvas, he posted an example of like a failure of Claro's theorem, like how the partial derivatives, the mixed partials can be different if you do them in a different order. It's a funky example, but it's kind of the easiest example. So have any of you looked at that? Let me pull it up real quick, just so you can see where it is. I think it's worthwhile. I mean, I don't think it's anything you really need to worry about, but I do think it is interesting and at least worthwhile to be like, oh, that's the kind of bizarre thing that doesn't meet this condition. Great. I don't have to worry about that ever. The log into Canvas, terrible. Well, that was almost really terrible. All right, let's see. 17C, where'd you go? There you are. And then if we look at the files, and let's see where the supplementary notes. You look here, there's the claro.pdf. If you look here, you see an example showing that the fxy is not the same as fyx, at least at a particular point. So here's like the easiest function someone's ever come up with where this mixed partial one way doesn't equal the mixed partial the other way. I would encourage you all to, if you have a minute, take a look at this. It's kind of interesting. It's not super important, but it is kind of neat. But there you can see, oh yeah, the easiest function where this thing doesn't work is some piecewise thing that's definitely very undefined or weirdly defined at the origin. All right. Any questions about all these second partial derivatives here? Definitely, I would say as far as moving forward with partial derivatives, because they're not going away, right? They're definitely going to stick. We're definitely going to be using first and second partials to find relative maxima and minima of and saddle points of surfaces. So keep practicing these. They're going to be there. Do the homework problems. The one main thing to remember is that when you're differentiating with respect to x, you're treating every other variable like a constant. You're differentiating with respect to y, you're treating every other variable like a constant, and so on and so on. Which actually brings up a good point. We should at least do one problem. Did I hide it from myself? Good, it's all right. I can make something up. We should do one problem where we have to use implicit differentiation. Let's do an implicit one. Let's try to make it not too ugly. Let me just steal one from the book. It's always a good plan. It's mostly usually a good plan. Let's see. I don't really care if it's a homework problem or not. So there we go. Yeah, sure. Let's look at something like that. Let's say we have, I'm going to change it up. Let's say we have x cubed plus y to the fourth minus z squared equal to, sure, 3x squared y z. That's going to be kind of gross. That's all right. And we're being asked to find del z del x. I'm just curious. Someone like just put on like some strawberry lip thing. It smells. I just. It's fine. It's not. I was just like, oh, I'm really getting a strawberry waft over here. It smells nice. I was just like, I didn't see it happen. So I'm like, what's going on? Am I just hallucinating smells? Okay, it's good. Good. I'm not hallucinating smells. It's good. Okay, so if we're gonna find del z del x, here's what we have to remember to think about. X is our variable. Z is a function of x. And y is acting like a constant. Which makes sense if we think about what del z del x really means. Del z del x asks you the question, how is z changing as x is changing? You know what's not changing in that sentence? Y. Right? As x changes, what's z doing? No one's asking about y. No one cares about y in this problem. So when we start taking derivatives, we're going to say, okay, great, y is going to be a constant as far as we're concerned. So taking the derivative of both sides, differentiating both sides. Derivative of x cubed is 3x squared. Derivative of y to the fourth is 0. And now here's where we have to be extra careful. Normally, you would think of just like if you're differentiating with respect to z, the derivative of z squared would be 2z. But since z is a function of x, or we're pretending like it's a function of x, z is our quote unquote stuff. And the derivative of some stuff squared is 2 times your stuff to the first power times the derivative of your stuff. Just like when we were doing implicit in 17a. When you did the derivative of y squared, you got 2 times y to the first times the derivative of y. On the right-hand side, it's even grosser because we have 3x squared times yz. We have to use the product rule because we have a product of 2 variables. So the derivative of 3x squared is going to be 6x. We're going to leave the other piece alone. Plus, now we change it up. We leave the 3x squared alone. And the derivative of y times z, well, y is a constant, so it's going to hang out. And the derivative of z is the derivative of z. Del z del x. And now we've done all the work of differentiating. The rest is just using algebra to solve for del z del x. So I see this term, let's use a different color, James. I see this term here that has a del z del x and this term here that has a del z del x. Normally, I would choose to bring all the del z del x's to the left just because that feels natural. But here I'm going to make the choice to bring them all to the right because it's going to keep everything positive. It doesn't really matter. I just like to make the choice where things stay positive if possible. So I'm going to bring all of my del z del x's to the right. So I'm going to get a 3x squared y del z del x plus a 2z times del z del x equal to, bring this to the left, a 3x squared minus 6xy z. I think you probably solve for del z del x in one step, but I'm gonna do it in two. I'm gonna first factor out a del z del x from the right hand side. So I'm left with 3x squared y plus 2z, still equal to the same left hand side of 3x squared minus 6 times x times z, 6 times x times y times z. And finally, divide by this thing over here to isolate del z del x. So del z del x is going to equal 3x squared minus 6xyz divided by 3x squared y plus 2z. That is as good as it gets. And then when we start talking about the chain rule, or I should say the multivariable function version of the chain rule, we'll see that there's like a tricky kind of faster formula for doing this kind of implicit differentiation thing, which is kind of neat. It's not super necessary, but it is kind of interesting. So that's how you deal with implicit. If instead we had been asked to find, we're not going to do it, but I'm just going to point out that if they said like, find del x del y, then we would have made the same sort of choices. We would have said, okay, well now y is our variable, x is the function that depends on it, and z is the thing that's a constant. So differentiating both sides this way, we would have gotten, so now the derivative of some stuff cubed would be 3 times my stuff squared times the derivative of my stuff. The derivative of y to the fourth would be 4y cubed. The derivative of z squared would be 0. And then on the right hand side, I would probably treat it as, no, I'd probably still treat it the same, 3x squared times yz. The derivative of 3 times x squared is 6 times x times del x del y times yz, plus then a 3x squared times the derivative of yz is just 1 times z. So it's a totally, I mean, it's not like that different, but it is a very different problem if you're asked to find a different derivative. You're treating different things like constants and variables depending on what they're asking you to find. Just be a little bit careful there. All right, let's talk about tangent planes / linearizations, which often are the same thing, but they're not exactly the same thing. We'll kind of talk about why they're not the same thing. Tangent planes and linearizations. And so let's cycle back for a second to 17a, where if you were going to find in 17a the equation of a line tangent to y equal to f of x at some point x naught comma y naught is given by, so the way we always find the equation of a line. Okay, always is a stretch there. The way we often find the equation of a line, which is y minus the y coordinate equal to the slope. And how do you find the slope of a function or of a line? Better question, James. How do you find the slope of a tangent line to a function at a particular point? We find the, how do you find the slope of the tangent line?
Right.
But what's the thing we spent like most of 17a doing? You use the derivative to find the slope of the tangent line. That's one of the main interpretations of what a derivative is. So it's the f prime of x naught times x minus the x coordinate. Or often written as y equal to y naught plus f prime of x naught times x minus x naught. The tangent line is just another name for the linearization of a function of one variable. The linearization of f of x of y equal to f of x at the point x naught comma y naught is the same thing. We just write it as L of x equal to, we actually usually don't write it as y naught. We usually write it as f of x naught for some reason instead of writing it as y naught. plus f prime of x naught times x minus x naught. You might use x naught, you might use a. Some people use a for whatever reason. I think this, I don't actually remember the way this book chooses to do it. But look, this equation is the same equation. This equation here and this equation here are the same equation because the linearization is the same thing as the equation of the tangent line. So for example, I need to move this piece of paper maybe. So for example, we could find the linearization of f of x equal to the square root of x at x equal to 15. No, 16. What am I? It's 15. I made a poor choice. That's not that poor choice. I'm gonna fix it. At x not equal to 16. In other words, find the equation of the line tangent to the square root function at the point where x is equal to 16. Let's draw a picture. So here's the picture of this thing. Here's my usual square root function. And right there. So that's where x naught is equal to 16. And there's my equation of my tangent line. And I want you to notice that near the point of tangency, the line, aka the linearization, is very close to the function, the square root function. But as you move further away from this point, either to the right or the left, these two curves start to diverge from each other, right? They don't stay close. They move further and further away. If you went way out here, right, they'd be very, very, very different. How do I find the equation this time? Well, I'm just going to use the linearization formula. So I'm going to say, I know that L of x is going to be f of 16 plus f prime of 16 times x minus 16. Just substituting in the value of 16 in the place of x naught. I still have to find the things though, right? So I need to know what f of 16 is. So f of 16 is going to be the square root of 16, which is 4. And f prime of 16, well, I need to find f prime of x. So f prime of x is going to be the derivative of x to the 1/2 is 1/2 x to the negative 1. Or as I would prefer to write, 1 divided by 2 root x. Same deal. So then f prime of 16 is equal to 1 divided by 2 times the square root of 16, which is 1 over 2 times 4, which is 1 over 8. So then we can go and actually write the linearization, aka the equation of our tangent line, as L of x equal to 4 plus 1/8 times x minus 16. And I will point out, it is usually in our interest to leave it this way. Meaning, I don't really want to distribute this 1/8 and write it as 4 plus 1/8 times x minus 1/8 times 16. 1/8 times 16 is 2. So 4 minus 2 is 2. So I could rewrite it as 1/8 x plus 2. It's usually not what I want to do. It's usually not helpful. Although I will point out, looking at the textbook answers in the back of the book, they do typically do that simplification. The reason it's not particularly useful most of the time is a lot of the time they're going to then ask you to use this linearization to then approximate a value of the function that's close to the point of tangency. For example, I could say, yeah, I want you to approximate the square root of 18 using this linearization. So here's what I know. I know that this linearization, L of x, is an approximation of this function, the square root of x. So what that really, really means for me is we're saying that the square root of x is approximately L of X. And L of X is 4 plus 1/8 times X minus 16. At least it's approximately that near X equal to 16, right? If we move too far away from 16, it's no longer a good approximation. But for values of X that are close to 16, I would say that 18 is close enough to 16 to be close. We can use this to approximate the value. So if I then plug in 18 for X, the square root of 18 is approximately the linearization evaluated to 18, which is going to be 4 plus 1/8 times 18 minus 16, which is 4 plus 1/8 times 2, 2/8, and 4 plus 1/4 is equal to 4.25. Most of the time I prefer a fraction, but here a decimal I think is nice, because then if you go and actually plug it into a calculator, you're going to get, you kind of compare and see how close were we really. So if you look at the square root of 18 on the calculator, it's going to be, let's see, the square root of 18 is 4.2426 approximately. So the square root of 18 on the calculator is approximately 4.2426, etc. So not bad, right? We're right to the first decimal. That's pretty good for a not too challenging approximation. The same idea we can extend to functions of more variables and instead of lines, surfaces and tangent planes. So instead of having a curve and a tangent line, we're now going to have a surface and a tangent plane to that surface. But the formula is going to look almost virtually the same, which is really nice. So I'm never good at drawing this picture. Let me just show you the picture that I'm not going to draw. So here's the idea. We've got some surface and there's a point on that surface and there's a plane that is tangent to that surface, meaning it's just touching the surface at that one point, and it's kind of like, you know, close to it near the point, and as they diverge from each other, it's further away. I'm trying to think of like a good example, but I'm not really like bring like any kind of thing that's oh here, we'll use this. Pretend like this is our surface, and we're having our point of tangency being right there, and here's our tangent plane. I mean, it's okay. And you can see that like near the point of tangency, the plane is really close to the surface, but as you move further away from the point of tangency, there's definitely some distance between the plane and the actual surface of the cylinder. So that's kind of the idea, is that we can use this tangent plane, just like we used the tangent line in the previous example, to approximate values of our surface near point of tangency. Let's look at what we've got here. So very similarly, the tangent plane to the surface z equal to f of x comma y at the point, instead of x naught y naught, now it's going to be x naught y naught z naught, is given by, it's literally the same idea. Instead of doing y minus y naught equals the derivative times x minus x naught, I'm just going to add in another thing. So now z is kind of the function thing instead of y. So it's going to be z minus the z coordinate equal to, there's not just one slope anymore though, right? It's not just f prime of x times x minus x naught. It's going to be the partial derivative with respect to x evaluated at the point, x naught y naught, times x minus the x coordinate, x naught. And then what do you think the next piece is going to be? I bet you could all guess it and fill it in. Instead of the partial with respect to x, I also need the partial with respect to y. Not time. At evaluated at x naught y naught, but now we're multiplying by y minus 1. I kind of think of it, it's kind of like you're finding the tangent line in the x direction, you're finding the tangent line in the y direction, and then the plane is the plane that includes both of those tangent lines in it. So it's the plane that has to have those two lines, which is kind of right. And then, just like before, if we want to find the linearization, you're basically just isolating the z part and then replacing it with L of the variables. But now instead of L of x, like it was in the previous page, it's going to be L of x comma y. So we're going to say that z will now be L of x comma y, and it's going to equal z naught, but we don't write z naught because I don't know, we choose to make it hard on ourselves. Z naught's going to be f of x naught comma y naught, which makes sense, right? If z equals f of x y, and we have the point x naught y naught z naught, we plug in x naught for x and y naught for y, we should get z naught for z. And then plus fx at x naught y naught times x minus x naught plus fy evaluated at x naught y naught times y minus y naught. It's very much the same formula as on the previous page. We've just added another dimension to it. Cool. Questions about this before we get into an example? All right, let's look at, yeah, I think we can get all this in here. So let's say we want to find the linearization of the surface f of xy equal to x cubed times y to the fourth at the point 2 comma 1. And then we're going to use that linearization to approximate or estimate f of 2.2 comma 0.9, which you could totally do. I mean, you could 0.9 to the fourth is a little bit hard. 2.2 to the third. Okay, you could totally do that with the calculator though, without 2.9. But in any case, we do edit with the calculator. So what's the point of saying that? So yes, we'll do an approximation, then we'll plug it in and see how good it is. So here's my linearization. I guess I should find my partial derivatives first. So my partial with respect to x is going to be 3x squared times y to the fourth. And if I plug in the point 2 comma 1, the partial with respect to x at 2 comma 1 is going to be 3 times 2 squared, which is 3 times 4, times 1 to the fourth, which is just 1. So that's going to be 12. Similarly, fy, the partial with respect to y, is going to be x cubed times 4y cubed. If I plug in 2 comma 1, fy evaluated at 2 comma 1 is going to be 2 cubed times 4 times 1 cubed, which is 32. Okay. So now I think I have almost all the pieces. The other piece I need is what f of x naught y naught is. So f of x naught y naught, so f of 2 comma 1 is going to equal 2 cubed times 1 to the fourth, which is 8. Here's something I usually think about when I'm doing these problems. The value I get, right? I plugged in 2 comma 1 and I got 8. When I plug in 2.2 comma 0.9, I shouldn't be too far off from 8, right? I'm not moving too far away from the point I plugged in, so the function value shouldn't change drastically, unless you've got some weirdly like discontinuous function, but that's usually not the case. So let's use this linearization formula. L of xy is going to equal f of x naught y naught, which we just found to be 8, plus fx at x naught y naught, which we found to be 12, times x minus the x value, which is 2, plus fy at 2 comma 1, which is 32, times y minus the y value, which is y minus 1. And again, I really can't see a good argument for multiplying this out and simplifying it. If it was the book, they probably would. They would probably rewrite this as, let's see, 12x plus 32y. And then the constant would be 8. And then 12 minus 2 is negative 24. Sorry, 12 times minus 2 is negative 24. And 32 times negative 1 is negative 32. So you have a negative 32 minus 24, which is negative 56 plus 8 would be negative 48. Right? There isn't a good reason to do this. There's actually this is actually going to make it harder, right? Because if I plug in 2.2 for x, 2.2 minus 2 is 0.2, and I know how to multiply 0.2 times 12. 12 times 2.2 is a little bit more mental energy. Same deal over here. 0.9 minus 1 is negative 0.1, and I can multiply that by 32 without too much effort. Whereas 32 times 0.9 itself, I don't know what 9 times 32 right off the top of my head is. So like it's easier if you don't simplify it this way. So now I'm going to say that f of 2.2 comma 0.9 is approximately L of 2.2 comma 0.9. I think it's nice to write this step here. It shows that you know what you're doing. You're saying, I want to get the function value. I'm approximating it using the linearization. And then we just plug 2.2 in for x and 0.9 for y. So I get 8 plus 12 times 2.2 minus 2 plus 32 times 0.9 minus 1. That ends up being 8 plus 12 times 0.2 plus 32 times negative 0.1. That's going to be, I'm running out of the room here. 8 plus 12 times 2 is 24. So 12 times 0.2 is 2.4. 32 times 1 is 32. 32 times 0.1 is 3.2, but it's negative. 2.4 minus 3.2 is negative 0.8. So 8 minus 0.8 is 7.2. Let's see what we would have gotten if we actually put this into the original function. 2.2 cubed. Give us some new batteries, I think. It's hard to see what's going on. And then times 0.9 to the fourth. Is 6.986 approximately. So not too bad. We're off by a little bit, but not like an extreme amount. Yeah. So the last thing I wanted to say here is that a linearization doesn't always have to be a tangent plane. It can be a tangent line, but it can even be a tangent like higher dimensional thing, which is hard for people to, I don't know how to visualize it really. But let me just give you in these last couple minutes here an idea of what I mean, because there's 1 or 2 homework problems that do ask you about this. Not like, they didn't ask you to think about it so much as just to do it. So here's what I mean. Let's say we wanted to find, we probably won't finish this problem, but let's say we're given that f of x comma y comma z is equal to x squared times z plus y squared times x. And we want to find the linearization of f at the point 2, 3, 1. Yeah, sorry. Yes, of course. Yeah. We're just going to extend the idea to another dimension. So all we're going to say is that our linearization of x comma y comma z is, well, first it's f evaluated at the point. And then it's going to be, instead of the 2 partial derivatives multiplied by the respective x minus x naught or y minus y naught, it's going to be the 3 partial derivatives. It's going to be fx evaluated at x naught, y naught, z naught times x minus x naught plus the partial with respect to y at x naught, y naught, z naught times y minus y naught plus the partial with respect to z at x naught, y naught, z naught times z minus z naught. Where x naught is 2, y naught is 3, z naught is 1. So we're just extending the formula by another term or dimension. So here, okay. So here our linearization at x, y, z is going to be f of 2 comma 3 comma 1 plus the partial with respect to x. So my partial with respect to x is going to be, let's write it down here. Fx would be 2x times z plus y squared. Fy would be 2y times x, fz would be x squared. So then we would take our 2, 3, 1 point and plug it into these. So that's kind of a lot. So we're gonna get 2 times 2 times 1 plus 3 squared times x minus the x naught plus fy is 2yx. It's gonna be 2 times 3 times 1 times y minus the y naught plus fz would be x squared, so it's gonna be 2 squared times z minus the z naught. And then you could calculate those things more. Like you could simplify that, but that's the idea, right? It's the same formula as before. We just added on another piece here. Or another piece here. So someone, if they really wanted to be cruel, could give you like a function of 5 variables, f of x, y, z, w, t, and then ask you to linearize it, and there'd be 6 pieces to it. The f of x naught, y naught, z naught, w naught, t naught, plus the partial of the one thing times that variable minus its coordinate, plus. So you have all the, but it's just the same stuff, just you keep on adding the next piece. Okay, that's all I got. I have office hours over in Dutton Hall. If I don't see you, or if I do see you, have a lovely weekend. See you all on Monday.
Thank you.
Wrong. And as I hadn't said already, do the homework. Do the homework, do the homework, do the homework. Do the homework. It's gonna be a song. Do the homework, do the homework, do the homework, do the homework, do the homework. Do the homework. It's how you learn it. If you don't do the homework, you won't learn it. If you don't do the homework, you won't learn it.